Hey guys, I'm Darren and welcome back to Level Up EE Lab. Today is the 5th episode I'm doing on the repair of this IP-20 power supply, and I'm going to pick up right where I left off from the prior episode and talk now about the circuit that I've designed for the overcurrent protection limiter. Let's get to it. I ended the 4th episode with some power dissipation calculations for an overload protection circuit. And I concluded that I wanted this protection circuit to shut down the power supply if the regulator has to drop the output voltage by more than 20 volts to maintain that constant current. And now here's the electronics that will achieve that. I'm going to use an op amp as a rudimentary comparator to monitor the voltage difference between VRAW and VREG, as I'm calling them here on the schematic. I'll use the output of the op amp to drive an NPN transistor, which then controls a relay. Now, just like with the Heathkit design, I'll use the normally closed contacts and place them upstream of the regulator stages. So when the op amp output goes high enough, the transistor turns on, the relay gets energized, and the contacts open. Beautiful. But now, how do I reset it after it trips? I'll replace the single pole, single throw reset switch on the front panel with a dual pole version. One set of the normally closed contacts will handle the connection to the load, just like on the Heathkit version, but the other will handle the 5-volt power to the relay coil. So flipping this switch drops power to the relay, which restores power to the regulator stages and thus resets the power supply. The switch really only needs to be a momentary double pole, single throw switch, but those are hard to find, so I'll probably just use the much more common double pole, double throw toggle switch instead. But note that I can't just drop the 5 volts to the relay. I also need to disconnect the load, otherwise the power supply would reset and just sit there and cook. Now regarding the op amp, a comparator would technically be a better choice, but because I've already got one OPA 310 op amp on the board, adding another one by using the dual OPA 2310 package is simpler. It saves having to add a second IC. But regardless of whether I use an op amp or a comparator, I do need to scale down the input voltages. Feeding 50 volts into a device expecting no more than 5 volts makes for a bad day. And getting the circuit to trigger on a fixed voltage difference is a little bit trickier than it may seem at first. Let's start with the easy part, scaling down VRAW for the non-inverting input. I can do that with a simple voltage divider made from R34 and R36 connected from VRAW to ground with the non-inverting input tapped at the middle. Now I'll explain a bit later the purpose of that capacitor C2. Scaling down VREG for the inverting input is a bit different because I need the inverting input to be higher than the non-inverting input until VREG falls to 20 volts less than VRAW. Sounds easy, right? Just put in a second divider from VREG to ground with the inverting input tapped at the middle and choose the resistor value such that the op amp inputs are equal when there's a 20 volt difference between VRAW and VREG. Well, that would work for only one value of VRAW, which is useless here. I'm showing a detailed explanation, so pause the video and study this proof if you are dying to know why it won't work. One way to fix this problem is to make the ratios of the two voltage dividers equal, then add a voltage offset to the bottom of R35, which I'm calling V sub N. Now the op amp inputs will become equal whenever the difference between VRAW and VREG reaches a threshold voltage, which I'm calling VTH, and the performance is now independent of the magnitude of VRAW. I'm showing the formulas here. It's really not terribly complicated, but there is a bit of algebra to get to the final formula right here. Now, I did get this solution from another good discussion over on EEVBlog, so I'm showing in the description of this video a link to that discussion thread. These formulas assume that V sub N comes from an infinitely stiff voltage source. Well, that's all well and good for theory, but I really don't want to add yet another voltage source just for this tiny portion of the circuit. But as it turns out, it doesn't have to be infinitely stiff, just significantly stiffer than the rest of the resistor divider network. Which leads to the actual solution, a third voltage divider. This one takes my already existing 5-volt supply and uses R37 and R38 to create V sub N. The values for the 6 resistors are flexible provided they meet some basic rules, starting with rule number 1. R34 must equal R22 and R36 must equal R35. Second rule is R34 and R36 must set a divider ratio that knocks the maximum value of V raw down to be compatible with the op amp. I'm powering the 2310 with 5 volts, so that roughly sets the upper boundary. And there's a similar requirement for scaling V-reg. Which leads to rule number 3. R37 and R38 need to be substantially less than the other 4 resistors to maintain the stiffness of V sub n, but also not so low as to draw excessive current from the 5-volt supply. The standard values I chose here meet all of these rules, but there are many more combos that would work fine as well. The same equations apply as before with one exception. This expression is only an approximation now for V sub n. The reason being R37 and R38 don't make an infinitely stiff voltage source. There will be some slight shift in V sub n that is dependent on their actual values, and to be precise, I need to take that into account. For the precision calculation, I could do an LT spice simulation, but I decided to go old school here and do it by hand with the aid of Excel. You can use Kirchhoff's laws to put together these 5 equations of 5 unknowns. There'd be more equations if I had to account for the op-amp input bias currents, but they're less than 30 picoamps, so I can safely ignore them. And once you put the equations into matrix notation, Excel makes solving them easy by taking the inverse of the coefficients matrix and then multiplying that to the matrix of the constants. These cells here are the results, which includes V sub n and the voltage at the inverting input. Notice that there's only about a 2% difference between the approximate and precise calculations for V sub n. So, probably wasn't worth the extra effort here, but sometimes you don't know until you spend the time and do the calculations. Moving on, the next step is to calculate how far V-reg needs to drop to make the op-amp inputs equal. Then the difference between that V-reg and V-raw will be the trigger voltage, which again should ideally be 20 volts regardless of V-raw. To do this, I type in the appropriate V-raw here, then type in various values here for V-reg until the calculated op-amp input values are equal. I can do this repetitively by hand and zero in on it, but a much faster way is to use the solver command in Excel, which I've done for all 7 of the course voltage settings that will need the overcurrent protection. And this is the table and graph that shows the results. Column D shows the calculated V-reg values for each course voltage setting, and column E shows the resulting threshold voltages. Now ideally all these threshold voltages should be 20 volts, but of course there is some error. Worst case, it's less than 2% off 20 volts. Not too bad. And separately, I calculated the effect of the op-amp input offset error, which is 1.4 millivolts worst case, which adds another 0.1% or so to this graph. So the bottom line is I can definitely live with the performance of this circuit. Oh, I almost forgot. I need to talk about capacitor C2. I added it to prevent a problem whenever V-raw increases quickly, such as during startup or during range changes. It will take some time for the regulator to respond to an increase in V-raw. Now, how much time and how large will the delta end up being between V-raw and V-reg while the regulator is responding? Well, I don't really know. There's some transient info in the datasheet, but not exactly what I'm looking for, and trying to extrapolate it to this scenario is a bit of a stretch. So just for the sake of argument, let's make some big assumptions here, like 10 milliseconds to respond to a step change in input voltage, then another 5 milliseconds to reach stable regulation. The real figures are likely to be less given the transient response, but let's at least run with these. I can mitigate against this by adding capacitor C2 at the non-inverting terminal. Here's what the simulation looks like for 0.47 microfarads. That gives me some daylight between the op-amp inputs. Now, if that turns out to be not enough, I think I can add a bit more without causing other problems. And this should be an easy thing to check after the build to confirm it's enough of a delay. If you stuck with me through these very technical episodes, I've covered every element on the block diagram that I'm showing shaded gray. That leaves just 3 more to talk about: a fixed current load and the 2 low voltage DC supplies. Let's look now at the details of this guy, the fixed current load. The 317 and all of its linear regulator cousins do require a minimum amount of current to maintain regulation. For many of the modern regulators, that current is a milliamp or even less for some devices, but the 317 HV is definitely old school. It needs 12 milliamps worst case at maximum voltage drop. But anecdotally, the 317 seems to work fine with 10 milliamps, and you might be able to push it as low as 5 milliamps, but just to be conservative, I'll build a circuit for around 10 milliamps. Now, if I were building a fixed voltage power supply, I could just use a resistor across the output. Now, I can't do that here. At the 5 volt setting, I need a 500 ohm resistor to get 10 milliamps, and it would dissipate only 50 milliwatts. Pretty reasonable. But I changed the power supply to 50 volts, that same 500 ohm resistor would draw 100 milliamps and dissipate 5 watts. So I need a better solution. Here's what I'm going with, a 4-component circuit built around the TLV431 shunt regulator. Now this is a handy little device, kind of like a fancy Zener diode with lots of ways to use it. This particular circuit is figure number 25 from the onsemi datasheet for building a constant current sink. I can feed my 5 volts to the cathode of the 431 and the base of Q6 through R40, which sets up a bias current for the 431 and a base current for Q6. The choice of R40 is not that critical, I just need to make sure there's at least 80 microamps flowing through the 431. The 431 and the transistor work together such that 1.25 volts is maintained across R26. So whatever value I choose for it will set the current, and the transistor will be turned on just enough to pass that same current out of its emitter to R26. I want around 10 milliamps, so a standard value of 120 ohms will work fine. Now the beauty of this circuit is the current will be largely stable regardless of the voltage at Q6's collector, as long as I don't exceed the VCE max rating. I chose the tip 31C, which can handle 100 volts, and it comes in a nice TO220 package. It's likely many other transistors would work here too. Let's see how it works. Back to LT Spice. No Excel spreadsheet engineering for this one. And look at how remarkably flat the current draw is over the range of voltage. It does drop off rapidly below 2 volts. There's just not enough voltage at that point to keep the 431 working. The power dissipation by the 120 ohm resistor is a constant 13 milliwatts, but the bulk of the heat being dissipated, of course, is in the transistor. At max voltage, it's dissipating 600 milliwatts, which it can safely handle without a heat sink. Now, just for giggles, I also ran a simulation from 20 degrees C to 60 C. I'm not sure how accurate the thermal models for the components are, but the datasheet does say the 431's 1.25 volt output is stable within 2% from minus 40 C to plus 85 C. And that's just the A version. There are 2 other versions even better than that. And these results look plenty acceptable. I was curious because I had modeled other solutions, including traditional current mirrors made from pairs of transistors, but those solutions proved to be much poorer performers with respect to temperature and voltage variation. Which brings me finally to the 2 DC power supplies. Now there's not much to talk about here. What I'm doing is taking the 7 volt AC secondary voltage that originally powered the current limiter and repurposing it to feed into a bridge rectifier and a conventional 5 volt linear regulator. I calculated this 1500 microfarad cap using the same methods that I used previously to determine the main DC power bulk filter capacitance. I've designed around 200 milliamps or so of capacity, which is more than enough to power the fan, the relay, and the rest of the minor current draws like the op amp and the current limiter resistor divider, and of course this guy, an LM7705 negative bias generator. I mentioned in the last episode that I need a slightly negative voltage for the constant current op amp in order to give it more headroom to pull down the 317 under the highest current load. All the stuff around it comes straight from the application guidelines in the datasheet, including this ferrite bead. It's there to improve rejection of the high frequency junk that might end up on the output. That is it for the detailed deep dive into the electronics design. And I apologize, I'm not going to get to the heat transfer calculations in this episode, but those will be the first item for the 6th episode in this series, along with going through the circuit board layouts for all of the components that I've talked about over these past several episodes, and fingers crossed, getting into the cleaning and tear down and preparation of actual construction for this project. So I hope you guys stick with me, and as always, I hope you're enjoying the content here on my channel. So until next time, bye for now.